A round-trip Mars mission doesn't take months. It devours 2 to 3 years of your life. And most people fundamentally misunderstand the timeline. The journey there consumes 6 to 9 months. But here's the brutal reality nobody warns you about. Once you touch down on Mars, you cannot immediately return home. You're physically trapped on the red planet for 13 to 16 months, waiting for Earth and Mars to crawl back into proper orbital alignment. Today we're dissecting the actual mission timeline NASA and SpaceX are engineering, the unforgiving orbital mechanics making this extended stay mandatory, and why this timeline completely transforms how we approach Mars colonization. Most people imagine Mars travel like a cross-country flight. You just point your spacecraft at the red planet and accelerate until you arrive. But interplanetary space operates on completely different physics. Earth and Mars orbit the Sun at drastically different velocities, creating a constantly shifting distance between our worlds. Earth races around, completing its orbit in 365 days, while Mars lumbers along, taking a ponderous 687 days. During closest approach, an astronomical event called opposition, the two planets align on the same side of the Sun, separated by merely 34 million miles. But when Earth and Mars sit on opposite sides during conjunction, that cosmic chasm explodes to over 250 million miles. The distance fluctuation alone exceeds the minimum journey distance, making timing absolutely critical. Your first instinct screams launch during closest approach when they're practically neighbors. But orbital mechanics brutally punishes this intuition. Launching straight toward Mars during opposition would be like leaping from a speeding car toward another vehicle that's already far ahead. You'd need catastrophic amounts of fuel to accelerate fast enough, then even more fuel to brake upon arrival to avoid overshooting the target entirely. With current chemical propulsion technology, this brute force direct approach consumes impossible fuel quantities. We're talking fuel mass thousands of times heavier than the spacecraft itself. Completely impractical. Hey curious, before moving on, be sure to subscribe to our channel clicking on the notification bell and leave us a thumbs up so you don't miss out on our daily videos. The HOHMANN transfer, the elegant solution. Instead of fighting orbital physics, space engineers embrace it, using an elegant trajectory called the HOHMANN transfer orbit. This centuries-old mathematical solution, discovered by German scientist Walter Hohmann in 1925, remains our most fuel-efficient path between planets. Here's how it works. We launch the spacecraft not directly toward Mars, but onto a carefully calculated elliptical path around the Sun. The spacecraft coasts for months using the Sun's immense gravity to guide its trajectory, gradually widening its orbit until it intersects Mars's orbital path at precisely the moment Mars itself arrives at that exact point. It's cosmic choreography requiring exquisite timing, like throwing a ball to meet a moving target months in advance. This method maximizes fuel efficiency by working with orbital mechanics rather than against them. The catch? This perfect orbital configuration, the ideal launch window, occurs only when Earth and Mars align in a very specific geometric relationship, and this cosmic alignment happens merely once every 26 months. Miss this narrow window for any reason, mechanical failure, weather delays, funding issues, and the entire mission gets postponed for over 2 years, waiting for the next opportunity. This slow, unchangeable rhythm of planetary motion dictates every aspect of mission planning. This perfect orbital dance, the HOHMANN transfer window, only opens every 26 months when Earth overtakes Mars in their cosmic race around the Sun. Mission planners cannot simply decide to go to Mars whenever they want. They must wait for this rare alignment. Recent launch windows occurred in July 2020 when NASA's Perseverance and China's Tianwen-1 launched, then again in September 2022. Miss this narrow window? Perhaps due to technical delays, budget issues, or launch vehicle problems, and the entire mission gets postponed for over 2 years. This inflexible rhythm dictates everything: spacecraft construction schedules, astronaut training timelines, international partnerships. Every aspect of Mars mission planning revolves around these rare launch opportunities. Using chemical propulsion, the backbone of current space technology, the journey to Mars averages 6 to 9 months, depending on the specific trajectory chosen. NASA's Curiosity rover took 8.5 months in 2012, Perseverance required 7 months in 2021. For human missions, the duration will be similar. Imagine your entire world shrinking to the volume of a small apartment shared with 4 to 6 crewmates for roughly 3 seasons on Earth. This journey assaults the human body relentlessly. First comes cosmic radiation. Outside Earth's protective magnetic field, astronauts face constant bombardment from high-energy particles, both solar radiation and galactic cosmic rays from distant supernovae. This exposure significantly elevates cancer risks and can damage the central nervous system. Current spacecraft offer minimal shielding. Then there's microgravity's insidious effects. Astronauts lose 1 to 2% of bone density per month as the body decides bones are unnecessary without gravity's constant pull. Muscles atrophy rapidly, especially in legs and back. The cardiovascular system weakens since the heart doesn't need to pump hard against gravity. Even vision can deteriorate permanently as fluid shifts toward the head, increasing intracranial pressure. The psychological toll matches the physical damage. Isolation from Earth, which appears as merely a bright star. Communication delays growing to 20+ minutes one way. The monotony of confinement. Constant awareness that help is months away in case of emergency. Astronauts will need unprecedented mental resilience. After nearly 9 months of trials, touchdown on Mars, the landing sequence succeeds. Humanity plants its boots in red dust. The world celebrates. You'd think the worst is over, but survival on Mars for over a year presents challenges that dwarf the journey. Immediately upon arrival comes a crushing realization. You cannot leave yet. Not for 13 to 16 months minimum. Remember the orbital dance. While astronauts traveled to Mars, Earth didn't wait. It continued racing ahead on its faster inner track. From the Martian surface, astronauts would watch Earth rapidly pull away in the sky. Attempting an immediate return would require swimming against a massive cosmic current. The fuel requirements would be astronomical, far beyond current capabilities. Some theoretical proposals suggest ultra-short surface stays of only 30 to 90 days. But enabling such quick returns demands extremely high energy trajectories, consuming massive fuel quantities, and dramatically increasing mission costs and complexity. Alternatively, astronauts could take a much longer, slower return trip, but this defeats the purpose of a short surface stay while exposing crews to more radiation and microgravity damage. Therefore, the only practical option is the long-stay mission architecture. Astronauts must wait patiently for approximately 500 days, nearly 18 months, for the planets to continue their orbits until Earth and Mars realign into a favorable configuration, opening the return window. This waiting period becomes by far the longest and potentially most dangerous phase of the entire mission. Spending 500 days on Mars means facing constant existential threats. Radiation becomes a permanent companion, since Mars's atmosphere is 150 times thinner than Earth's, and the planet lacks a global magnetic field to deflect cosmic particles. The surface endures radiation levels unsustainable for long-term human habitation. Habitats need heavy shielding, possibly buried under Martian regolith for protection. The atmosphere itself, 95% carbon dioxide, is completely toxic. Any catastrophic life support failure or spacesuit rupture during extravehicular activity means death within minutes. Atmospheric pressure is so brutally low that without pressurized suits, exposed bodily fluids like saliva and tears would boil and vaporize even in freezing temperatures. It's an environment where survival depends entirely on technology functioning perfectly for 18 months straight. Then there are the infamous planet-wide dust storms. Not localized dust devils, but massive events that can envelop the entire planet for weeks, blocking sunlight completely. This fine abrasive dust infiltrates mechanisms, damages scientific equipment, and most critically, covers solar panels, cutting off the base's primary power source. Serious NASA mission proposals already consider small nuclear fission reactors as the primary power system, ensuring the base keeps running even during the darkest storms. With such overwhelming challenges, why even attempt Mars colonization? The answer goes beyond scientific curiosity or national prestige. Mars represents humanity's best backup plan for long-term survival. Earth faces existential risks, asteroid impacts, supervolcano eruptions, climate catastrophes, even self-inflicted threats like nuclear war or pandemics. Becoming a two-planet species dramatically improves humanity's odds of surviving cosmic-scale disasters. Mars offers unique advantages among solar system bodies. It has a 24.6-hour day cycle, nearly matching Earth's. Water ice exists in substantial quantities at the poles and underground. The atmosphere, though thin, provides some radiation protection and contains resources for fuel and oxygen production. Surface gravity at 38% of Earth's is challenging but potentially manageable for long-term human habitation, unlike the Moon's mere 16% gravity. Beyond survival insurance, Mars colonization drives technological advancement across countless fields: life support systems, renewable energy, resource utilization, radiation shielding, closed-loop agriculture, autonomous robotics. The innovations required for Mars will revolutionize life on Earth. Additionally, Mars exploration may answer profound questions. Did life ever emerge there? What happened to its ancient oceans and thick atmosphere? Understanding Mars's climatic collapse could provide crucial insights into planetary habitability and Earth's own climate future. Supporting humans on Mars for 18 months demands staggering resource quantities. Each astronaut needs approximately 2 pounds of food daily. That's 1,095 pounds per person for 18 months. For a crew of 6, that's over 3 tons of food alone. Transporting this from Earth costs roughly $10,000 per pound to Mars' surface. That's $65 million just for food for one crew. Water presents even greater challenges. Humans require about 1 gallon daily for drinking, cooking, and hygiene. That's 550 gallons per person over 18 months. Water weighs 8.34 pounds per gallon, so we're discussing 4,587 pounds of water per astronaut. For 6 crew members, that's 27,522 pounds, or nearly 14 tons. Shipping costs would exceed $275 million. This is why Mars missions must implement aggressive water recycling systems, recovering 90 to 95% of water from all sources, including urine, sweat, and humidity. Oxygen requirements add another massive burden. Each person breathes about 1.8 pounds of oxygen daily. Over 18 months, that's 972 pounds per astronaut. For 6 crew, that's 5,832 pounds. Fortunately, Mars's atmosphere, being 95% carbon dioxide, enables in situ resource utilization, ISRU. Systems can extract oxygen from the atmosphere and from subsurface water ice, dramatically reducing what must be shipped from Earth. Total mission costs reach astronomical figures. NASA estimates a first human Mars mission could cost $100 to $200 billion when factoring in spacecraft development, launch vehicles, habitats, life support, power systems, rovers, return vehicles, mission operations, and crew training. SpaceX founder Elon Musk suggests costs could drop to $10 billion per mission using fully reusable Starship vehicles. But even optimistic estimates put the price tag in tens of billions, requiring sustained political will and international cooperation over decades. Wait, you might be thinking, this sounds absolutely impossible. Maybe we should just give up on Mars entirely. But here's the thing. Despite these overwhelming challenges, we're closer to Mars than ever before. SpaceX is actively testing Starship. NASA's Artemis program is building the infrastructure. International space agencies are collaborating. The technology, the will, and the timeline all exist. So stay with me, because what comes next, the return journey and final timeline breakdown, shows this impossible mission is actually happening within the next 10 to 15 years. After approximately 500 exhausting days on Mars, celestial mechanics finally cooperate. The orbital dance realigns Earth and Mars into the ideal configuration. The return launch window opens. Astronauts board their ascent vehicle, lift off from the Martian surface, dock with the spacecraft waiting in orbit, and begin the final, bittersweet leg of their journey home. The return trip essentially mirrors the outbound journey, another 6 to 9 months of confinement facing the same deep space hazards. Cosmic radiation bombards crews already weakened by 18 months of Mars's partial gravity and accumulated radiation exposure. Microgravity again attacks bodies that have partially adapted to Mars's 38% gravity. The readjustment will be brutal. Astronauts must prepare mentally for months more of isolation, knowing Earth grows closer but remains unreachably distant. Let's calculate the full mission duration. First, there's 6 to 9 months traveling to Mars. Then the mandatory 13 to 16-month surface stay, approximately 500 days, waiting for the return window to open. Finally, another 6 to 9 months journeying back to Earth. Adding everything together yields a total mission duration of 26 to 34 months. That's 2 years minimum, potentially stretching to nearly 3 full years, almost 1,000 days away from Earth. A Mars mission isn't a simple expedition. It's a life commitment, a voluntary exile consuming years of your existence. This completely transforms mission planning, astronaut selection, psychological preparation, technological requirements. Crew members must be selected not just for technical expertise, but for extraordinary mental resilience. Families will be separated for years, careers put on hold. Entire lives dedicated to this singular endeavor. The first Mars astronauts will become some of history's greatest explorers, but they will pay an immense personal price. So there you have it. A round-trip Mars mission consumes 2 to 3 years due to the unforgiving realities of orbital mechanics. But here's a mind-bending question. What if Mars isn't actually humanity's best option for colonization, and there's another destination in our solar system that might be even more suitable? Check out my video on why it would be preferable to colonize Titan instead of Mars, where we explore Saturn's largest moon with its thick atmosphere, liquid hydrocarbon lakes, and surprisingly hospitable conditions.